Hi everyone, my name is Donghyun from Sogang University, South Korea, and advised by Professor Youngjae. And this talk, I will present a multi-tenant key value SSD with namespace and performance isolation. Key value store is a type of NoSQL database which uses simple key and value interface. For example, LocksDB and LevelDB are host-side key value store. On the other hand, key value SSD runs storage engine of key value store inside the SSD. The application that uses a key value store performs right through a thick host I/O stack, including indexing layer of storage engine and file system layer. But host file system's huge overhead has been reported, so to minimize this overhead, many studies have been trying to offload and implement storage engine of database inside SSD. And only with a thin host I/O stack, key value SSD has a benefit in terms of performance. In particular, low-structured merge tree-based key value SSD have been proposed recently. So I'm going to first introduce a concept of LSM tree. LSM tree is a hierarchical structure that consists of name table and SS table. If put requested with key K and value V from the host, will be appended to value log for persistence. Value log offset where V is stored are temporarily stored to mem table along with the key. When mem table is full, a set of key and value log offset are flushed to NAND flash memory in the form of SS table. In SS table, Bloom filter data structure is added for fast key search. And this SS table can be structured into multiple levels. If certain level SS table is full, then LSM tree chooses victim SS table of a next level that has overwrapped key range and reads them, and then they are merged into a new and big SS table one, and it is written to flash memory as a next level SS table. Then victim SS tables are invalidated. If get requested, key value search begins at mem table first. If not found, then key value search begins at SS table. If key is found, value is accessed by a log offset. Then value is retrieved. But there are two problems in current LSM tree-based key value SSD. First, current key value SSDs lack the multi-tenancy and namespace isolation support. Unlike single-tenant environment, the concurrent users are provided with their own dedicated server in a multi-tenant environment. Providing independent server to each user requires isolation in terms of security, privacy, and performance. These requirements can be met based on namespace isolation. The namespace isolation is to separate key value data of tenants into logical groups. However, current LSM tree-based key value SSDs do not support namespace isolation. Second, key value SSDs have difficulty in providing the promised read performance that storage device can provide. This is because multiple key value data of tenants are still managed by a global shared single LSM tree. Global shared single LSM tree hurt read performance. There are two reasons. First reason is most key value data is filled down to upper level of the LSM tree due to other key value tenants data. So most key value data will be indexed at upper level. Second reason is it must read Bloom filter from NAND flash memory several times. LSM tree search algorithm needs a lot of Bloom filter reads for key value data, which is indexed at upper level. So currently, per tenant read performance is limited. We confirmed this overhead in our motivation experiment using ILSM, which is a recent KV SSD, and we set up two read scenarios. First, when only tenant access key value data occupies our LSN tree. And second, when LSN tree is shared by tenant access and wise their own key value data at the same time. In case one, 60% of tenant access key value data is retrieved within 2 milliseconds. But in case two, 40% of tenant wise data is retrieved within 6 milliseconds. The first reason is 67% of tenant access key value data are fed down to the next level of index. And second, the number of Bloom filter rows are increased by 77%. Therefore, we set up these design goals for multi-tenant key value SSD. First, it supports namespace isolation, and it minimizes the read performance overhead. To this end, we propose ISO key value SSD satisfying these two goals. This shows overall architecture design of ISO key value SSD. First, this namespace information is transferred from the host and stored at mem table and SS table along with the key. And ISO key value SSD allows key value data access only if the matching both key and namespace are satisfied. Next, ISO key value SSD employs the per namespace dedicated LSN tree design. In mem table and the lowest level L0 SS table, key value data of tenants are mixed and stored all together. On the other hand, in other level SS table, key value data is separately stored based on namespace. This approach was designed for two reasons. First, the performance degradation caused by both a shared mem table and L0 SS table is negligible because only few key value data are indexed as shared regions. And second, mem table provisioning per namespace approach requires additional DRAM space. If the number of tenants increase, more DRAM capacity is required, which is not suitable to DRAM constrained key value SSD. The main effect of the per namespace LSN tree is that it prevents key value data from being indexed at upper level of the tree. So ISO key value SSD can control access based on users' namespace information and reduce key value data's access latency. This shows a namespace isolation mechanism that substantially segregates key value data into per namespace LSN trees. This mechanism runs with existing background compaction. It first reads L0 victim SS table. Then ISO key value SSD checks key range per namespace. In this example, there are 4 namespaces in victim SS table, so 4 key ranges are identified. Then ISO key value SSD read L1 victim SS table for merge. And during compaction process, it segregates key value data into independent SS table based on namespace. Then they are stored per namespace dedicated LSN tree. Because this mechanism aligns with existing background compaction, it segregates key value data without huge overhead. We prototype ISO key value SSD on FPGA-based SSD platform. Using put and get synthetic workloads, we compare ISO key value SSD with the baseline. Left figure shows that ISO key value SSD outperforms the baseline in terms of get performance. Particularly when the number of the tenants is 8, ISO key value SSD shows 2.9 times higher get throughput than the baseline. Because ISO key value SSD reduce the depth of LSN tree as well as reduce the Bloom filter rows during the key value data search. On the other hand, right figure shows that put performance of both systems are similar. To see the impact of per namespace LSM3, we measure CDF on which level of index of LSM3 is searched during get. In baseline left figure, as the number of tenants increased, the number of searches from the upper level index increased. For example, the percentage at which key value data is searched in L2 SS table is around 70%. This is due to a global shared LSM3. On the other hand, in ISO key value SSD right figure, key value data search is completed with only indexing of mem table and L0 and L1 SS table, regardless of the number of tenants, because key value data from other namespaces are indexed to individual LSM3s. Also, we measure how many balloon filter roles are performed during get, particularly when the number of the tenants is 8. ISO key value SSD result in 3.6 times fewer balloon filter roles than the baseline. We propose ISO key value SSD, which identifies the user's namespace information and manages the key value data using per namespace LSM3 design. ISO key value SSD not only provides strict view to each tenant, but achieves read performance benefit. Thank you.